Thanks for coming. Morning, everyone. This is a Uber talk. Let's get started. Actually, I'm very sad to see we have fewer and fewer people in the DataWorks Summit this year. So, but one thing is this is probably our last talk in the DataWorks Summit. So we also get something from this talk. Today we will talk about the geospatial data analytics platform at Uber. And it's me and also my colleague Lou, who's sitting there. He will join me later in the talk. Here's the agenda. First, we talk about some advertisement about Uber. The Uber company value, how's our business going, how's our systems going, everything company-wide. Then we talk about our data infrastructure at Uber, how we process the data, how's the big picture looks like, and where does all the SQL engines or geospatial platform fits into the big picture. Then we focus on the Presto part, which is an interactive SQL engine. We use it in production for a few years, which we invested in a number of features for that. And then we come into the geospatial specific things. Since a large number of the queries at Uber is geospatial, we need to know where the location is, how can we represent the rectangles, polygons, all these slightly different SQL concepts. And then Lou is an expert on that, and he will explain all these things. And then we talk about our work, how we do geospatial optimizations, actually making these queries faster, more reliable, and more easy to use for our internal customers. And then we share our roadmap. OK? The first chapter is about Uber. Uber has a mission, which is making the transportation as reliable as running water everywhere for everyone. So the transportation is not only for you take some Uber, some driver comes to pick you up, but also we have Uber Eats. Probably, I wish a number of you may already using that. Our Uber Eats business growing really fast, which is also building on the same taxi driver platform. And also we have Uber Freight, which is another business. And we have some Uber, the automated driving car, and a number of other things which you can also get some news about that. A few stats about the company. We are operating in 6 continents, over 70 countries, over 400 cities, I think maybe around 500 now. And globally, we have over 12,000 employees. And every day, we are supporting more than 10 million trips. And every month, we have over 40 million active riders. And each month, we have over 1.5 million active drivers. So and all these numbers are also growing really fast. Here is the whole big data infrastructure at Uber. You can see that from the left-hand side, we have 3 data sources. One is the Kafka, which stores all the events. Let's say something happened, you are calling for Uber, and then a driver got a signal, a driver pick you up in the airport, and then you get on the car. All these things are events stored in Kafka. And also another data source is from in-house built data store called Schemalis, which stored all the trips information, the most critical information. So Schemalis is, from the name you can see, it doesn't have a schema. It is actually sharded MySQL stored in JSON files, with serving our online storage and all the trips information. And internally, we also have many different other relational databases, including, for example, MySQL or Postgres and a number of others. All these data sources are finally dumping into our Hadoop data lake on the HDFS. In between, they are streaming jobs running. For example, the Pinot, Samza, all the jobs are running. And also, we load some of the data into MemSQL for real-time processing. So after these streaming jobs, and then finally we get all this data stored on HDFS, we have 2 kinds of tables. One, this data firstly arrive on HDFS. It doesn't do any pre-processing. It is highly nested. In Uber, it's very not uncommon to see over 30 levels of nesting. So you have a struct inside an array, inside a map, inside another struct. All these things are nested. And these are no cleaning. So you may see a huge number of null values there for all this. We call this raw tables. They are also registered to the Hive metastore. So all the data are finally on Hadoop. And on top of that, we are using Hive, Presto, and Spark to query this data. Currently, usage is like Hive and Spark, mostly for ETL, transforming and cleaning the data. And Presto is mostly for interactive queries. So the ETL jobs are running on Hive and Spark. And finally, we clean the data and get a small set of, we call it model tables, which are flat. There's no struct array or map there, and with lots of pre-join, pre-aggregations there, and also with so many data cleaning. So we do not have much of noise in the data. And both raw data and model data can be queried in Hive, Presto, and Spark. And finally, the small set of model tables will be loaded into a commercial database. That is for if you really want to run fast performance on this small set of data. Load it into that commercial database, and then some users query directly on that. On top of that, we are supporting a number of applications, including machine learning jobs, real-time applications, reports, ad hoc queries, BI tools, all these things. And we are doing cross-data center all active. We have a number of data centers. Also, we are supporting security, the GDPR, which is Uber has another talk yesterday talking about the GDPR security, all the things, how we enforce them in all of the whole system. Also, we are doing observability and cluster management for all these things. And the data format at Uber. As I mentioned, we have two sets of tables. One is a raw table. All the raw tables are no pre-processing, highly nested. And but the data latency, when do they arrive on HDFS? It's quite short. It's just around 30 minutes. And this table are surely pretty huge, really huge tables. And they are stored in Parquet format. We choose Parquet because from design, at the very beginning, Parquet is targeting for the highly nested data. So we choose these. And the other set is model tables, which is with pre-processing, running on Hive and Spark. It's flattened, no nested structure there. But the data latency is much higher. It's over 12 hours, since we need to first run the ETL job. And we also, if you are choosing to use a commercial database, I need to load into the database, which also costs a few hours. And all these data are stored in ORC format. So I think one interesting question is why we have different formats for these two. Although ORC and Parquet are both open source columnar storage, very good quality. I would say because historically, the commercial database can only load ORC tables. So we have to store them as ORC format. Yep, that is an introduction for Presto. What is Presto? Presto is an interactive SQL engine for big data. And I'm lucky to see Martin, who is a founding father for Presto from Facebook. He's also sitting here. So for all the Presto internal questions, he knows much better than me. Yeah. And Presto provides interactive query speeds, which is if you try it, you will see it's much faster than Hive. You will like it. And Presto is horizontally scaled. So let's say you have 100 machine cluster, and you just got another 50 machines. You can just install software and then plug them in. No need to maintenance, no downtime, and no restart for the cluster. You just horizontally scale. And it's very common for us, Uber, we have hundreds of machines, single cluster. The biggest cluster is hundreds of machines. I think Facebook may have a bigger scale as well. Presto supports standard SQL. ANSI SQL is very close to standard SQL, and we try to make them as close as possible. So everyone knows SQL, and it's easy to use. Also, it's created by Facebook and battle tested by Facebook, Uber, Netflix, Pinterest, Airbnb, LinkedIn, Twitter. Yeah, I even cannot think of their company not using Presto. I will love it. Completely open source. You can see that there's a GitHub. You just search for Presto, you will see there, and you'll see so many activities there, including everyone's either posting a patch or making new features and so many fixes, very active. And also, Presto has a nice design. You can run SQL on top of not only Hadoop, the HDFS, but also you can run SQL on a number of other storage solutions, including, for example, we are using Elasticsearch, SQL on Elasticsearch, or SQL on Cassandra, SQL on Kafka, SQL on MySQL or Postgres. Why are we doing that? Since you do not need to copy the data from MySQL into Hadoop. You can just join the data. One table from MySQL, another one from Hadoop, or join another one from Elasticsearch index, so you can do everything for that. A quick introduction about internally how Presto works. So each Presto cluster has one coordinator and a number of workers. All the others are workers. The user sending a SQL query into coordinator, and there's a analyzer generate the AST, and now we have the planner generate the logical plan. We have optimizations, rule-based optimizations, and now just in a few weeks ago, Starbucks company also released a cost-based optimizer for that. So there's a following talk for that. Then Presto chunk it up into different fragments and make sure all the query can be parallel executed. And then there's a scheduler and node manager to schedule all these tasks on the threads on the workers. And also the node manager will track the node status, all the worker status, and also the task status. I know which one is failing, which one is running, what are the states it is running. On each of the worker, they may scan some files from a storage solution. Most commonly used is the Hadoop. You can just read a file from Hadoop, like what MapReduce or Hive did. But you can also read some data from MySQL, Elasticsearch, Pinot. These are the things Uber is using in production. It's common for our customer. They can join one Elasticsearch table with a Hadoop table, or join a Hadoop table with a MySQL table. It's a very common use case at Uber. And then after scanning these files, Presto will run the SQL aggregation, or group by all the SQL operations, and finally streaming the result to the client. About how Presto used at Uber, it's in production for over 2 years. And now in each data center, we have 2 clusters. One is we call application cluster, which is very time sensitive, so for low latency queries. Composed of hundreds of machines, serving more than 150K queries per day, and the P90 for that is under 20 seconds. Another one is a shared, it's a everything cluster. Everyone can just shoot a query the year. Also composed of hundreds of machines and serving over 50K queries per day, and the P90 for that is under 60 seconds. So all these two clusters together, we are serving over 200K queries per day, and Presto can query any data, either raw table, model table, data in MySQL, or all the other storage solutions. The applications we are supporting at Uber, including the computing the real-time driver incentives, because Presto is super fast, so we are supporting that application. Also, communication platform will try to detect the bad drivers, or bad riders, maybe, and doing that. Also, supporting the BI dashboard, data science, data exploration, also the data quality tracks. When we are ingesting the data, we need to check the quality. And so many others, just some data scientists or anyone have an idea, well, what can I get from this data? You just shoot an ad hoc query, and the performance in Presto is good. Why Presto is fast? I just list a number of reasons. Number one is in-memory processing. So Presto only tasks this once. So once reading the data from HDFS or Elasticsearch or Pinot. This is the only time Presto hits disk. Yeah, I will introduce a new feature in the following slides about that. But currently, only hit disk once. All the following processing are in memory. So it's in-memory is generally very fast. Also, Presto is pipelining and streaming. Unlike the MapReduce model, which is a push-based model, Presto is a pull-based. So if you are shooting a limit query, let's say I want to get the limit 5 result for this SQL, MapReduce will compute everything and then push it to the top level operators, and then they select the 5. But Presto is pulling, give me the top 5 results. Whenever I get the 5 results, then I'm done. I will release all the resources for this SQL. So it's much faster than the old pushing-based model. Also, Presto supports columnar storage and columnar execution, which means the data on disk Presto supports ORC, Parquet, all these columnar formats. And also in memory, Presto is doing the vectorized execution. All the data is for the same column is encoded and compressed. And there's an internal evaluation, expression evaluation, can evaluate all these values vectorizedly. That makes Presto faster than all the other in-memory engines. And Presto doing so many of the bytecode generation for almost all the operators, including inline virtual function calls, inline the constant, so that we get rid of the jump between the constant zone and the code zone. Also rewrite the inner loops, also the type-specific branches. All these things are supported. A few words about resource management. We are not using Presto on Yarn or on Mesos. We just, Presto itself has its own resource manager called resource group. For CPU management, internally Presto have priority queues. So the key idea is whenever you shoot some query, Presto try to give you the highest priority. Let you consume much resource as possible within a short period of time. If you still cannot finish, then you are put into the next level priority queue. If you are still cannot finish after a while, you are the lowest queue. So like the CPU sharing. And the memory management is, since all the data, the processing is in memory, so there's one configuration. It's important for max memory per query per node, which means how much memory each query can consume on each of the workers. So what if the query exceeds that memory limit? Presto will kill the query, saying your query exceeds the memory cap, but there's no OOM. I mean, Presto keep track of the buffer size, and if you are bigger than that, kill the query, but no OOM for that. There are limitations as well. Number one is from the design, Presto doesn't have fault tolerance. I do not know of any work of planning of supporting that. So if in the middle, let's say one of the workers is down for any reason, all the queries that having tasks running on this worker, that query will fail. So the philosophy is like, since Presto is fast, even if you retry your query a second time, it is still faster than running it on MapReduce. Since if you are running on MapReduce, you schedule another fault tolerance backup task, but they are spinning to disk and so many things. So even if you retry your query, it is still faster than schedule the backup and fault tolerance. And from our experience, we see that our customers are trained so that sometimes if one or two nodes are down, they just retry themselves, and they do not buzz us for any help. So that's OK. What if the join doesn't fit in memory? If you are joining two huge tables, although Presto supports distributed hash join, but still, what if the bucket is still a memory limit for that? Presto will kill the query, and no OOM, but your query failed. So one feature currently merged in open source is spill to disk, trying to support that if there's a memory is a limit, we try to spill the intermediate result on disk, and then you can the whole query will succeed, although the latency may be slightly higher. Our current solution is suggest user to try it on Hive. So whatever you first try it on Presto, a small portion of that you cannot run on Presto, try it on Hive. One other thing, the coordinator is a single point of failure. You will see that there's only one coordinator in Presto cluster. If that coordinator failure, I think we saw once during our 2 years deployment, and for maybe a few minutes. So if there's a coordinator failure, then the whole cluster is down. So this is a single point of failure. One more words about Presto connectors. I think this is really a nice feature, and it's very popular at our company. If you are trying to join data from different sources, you do not need to copy the data. Presto just push the compute to the data instead of copying the data here and there, since copying the data is always very expensive. So we have so many connectors open source, including the Hadoop connector, Postgres, Mongo, MySQL, Kafka, Cassandra, Redis. And Uber will build Elasticsearch for that. So here are a few things what Uber developed for Presto. Number one thing is for Parquet optimizations. We did a number of, since more than 80% of our data are in Parquet format, And I know Facebook is using ORC. And we try to optimize Parquet as much as possible. And now we get a decent performance for that, including the nested column pruning, column arrays, lazy arrays, predicate pushdown, and using the dictionary to help evaluate the predicates, all these things. And the geospatial optimizations, which Lou is working on that. He will talk about all the details about that. Also, the name node optimizations. Since our name node is shared by Hive, Spark, Presto, all these jobs are consuming the name node RPC. It's very easy for a single name node to become a bottleneck. And we are making a few optimizations so that we reduce the number of name node RPC calls inside Presto. One other thing is we build a Presto Elasticsearch connector from scratch so that our customers can join data between Hadoop, Elasticsearch, Pinot, and MySQL. There's no data copy. Yeah, that's all for me. And my colleague Lou will talk about all the geospatial work we did.
Hi, everyone. So I will be all focusing on the geospatial part. So when we design the geospatial analytics platform, so we have 3 requirements. First, efficiency. We want the query to run as fast as possible. Second, reliability. So the query need to succeed most of the time given our data scale. Third is usability. So we all the things need to be easier for user to onboard and use. So first, let's look at what the geospatial data Uber has. So for example, we have the geospatial data for each city. And each city could be further divided into sub-areas. For example, like Bay Area, you can get divided like Palo Alto, Sunnyvale, San Jose. And also, we have the spatial data for points of interest, such as Levi Stadium, AT&T Park, and Oracle Arena. Also, more importantly, we have the trips data. So as Zheng Xiao just mentioned, so Uber has 10 million trips every day. And for each trip, we have the started at point and started at location, the drop off location, and also the GPS data along the trip. So how we store the geospatial data? So basically, one basic data structure is point, right? So it's just a basic longitude and latitude pair. And for example, each trip, the started at and the drop-off location of each trip. And also the polygon. So the polygon is stored as a series points representing the boundary of this geospatial area. And so internally, we call it a geofence. So here's a very basic geospatial query. And so we want to get, for each city, for each airport, we want to know how many events happened on the specific day. So here's a query. So you select the airport code count star from 2 table joining the event table, join the airport table, and the join condition is geospatial function SD contains. So it will return true only if the points is inside the geofence. So here's how it is computed without optimization. So basically, the ST contents need to run for each pair of point and geofence. Then the computation complexity is essentially linear to the number of vertices in the geofences. And for some geofence, the shape could be very complicated, containing huge number of points. So then that's why the computation complexity could be huge. And here's an example. So if you have 2 billion events times 200 airports, then the computation cost could around 40 weeks. So how we improve the efficiency here? The idea is simple. We index the space. So here we use Quadtree. We use Quadtree here. Quadtree is one kind of space partitioning tree, and for each node, each node could divide the space into 4 parts: the northwest, northeast, southwest, and southeast. And using Quadtree, you can easily targeting to the bounding box that contains the geofences you are interested in. So here's just an illustration how you partition the space of San Francisco. Then we start building this optimization in Hive. So we have a service specifically for building Quadtree index. And from the user, if they want to apply this optimization, they need to rewrite the query, use the set configuration and some Quadtree UDFs. I will show the query later. And during runtime, on the Hive server 2 side, the Hive hook will detect this Quadtree UDF and send a request to the service. And the service will build the Quadtree and send that back, and then a temporary Hive UDF will register, and then the query runs with this Quadtree optimization. So here's an example. So on the left side is a query before, on the right side is a query after. You will notice the difference here. So you have to specify which table you want to use and which field contains the geospatial data, and also use the UDF in your actual query. So then we have this optimization in Hive. So on the efficiency side, we can achieve 15 times speed up, and the query used to run in 5 hours can finish in 20 minutes now. And can we get even faster? And on the other side, we actually satisfy the reliability and the usability a little bit. So on the reliability side, so we import the external service dependency. So the service could go down, and because you send the request to the service, actually the service run a Hive query and build the index, and during this query compilation time, so the call could time out sometimes. And on the usability side, so user need to rewrite the query, and user need to learn how to rewrite it as, and there's certain learning curve. So can we improve the reliability, usability, and further improve the efficiency? Then we start implementing the same thing in Presto. And on the efficiency side, can we get more speed up in Presto? And on the reliability side, so if we have that in Presto, we don't have external dependency. And Presto has this plugin concept. You can implement your own UDFs there. And also, in this way, the indexing stage and the query stage actually happen in the same place. On the usability side, we don't want the user to rewrite the query. So we can implement the query optimizer to automatically rewrite the user query, use this Quadtree feature. So here's the same query, right side, left side query before, the other side query after. So we optimize this query, use the new the Quadtree related UDFs and cross join, and so when user run the query, is essentially the same query, and but it comes to Presto. Presto will we have this optimizer could automatically rewrite the query, and the query runs with this geospatial indexing feature. In the runtime, the Quadtree is built through this build geoindex UDF, and this index will broadcast to all workers. And then when the other UDF SD contents is running, it will leverage this Quadtree index to first get the candidates in the bounding box, and then we only run SD contents for a small number of candidates. So here's a benchmark you run comparing the Presto and Hive, and so you can easily see we achieve 5 times speed up in Presto, and also we saved more CPU resource here. So some future work. So there's a limitation in this. There's a limitation in this implementation because we have to build the whole tree and broadcast it to all workers. And if the index is huge, then it's gonna hit memory issue. So we want to implement the distribute geospatial join here. Also, we want to integrate with H3. So H3 is a Uber open source technology. Is Uber's way to partition the whole world into hexagons. And so on the serving side, so all Uber services use the H3, but on the analytic world, we sort of use the geofences and the polygon, and there is a request to integration with H3, and then we can achieve better performance here. And also, we want to support interactive geospatial analysis workflow. So as you see here, so all the geofences using here are predefined. So we want to support this UI that you can draw a random geofence, and automatically it will build index and upload related stats to the analysis. All right, so we are actively hiring. So if you are interested, you can send a resume to me and Zheng Xiao. All right, that's it. Yeah, any questions?
No questions, we are done. Thank you.